Hi. On this first video, I would like to review theorems related with vector fields and to apply these theorems to obtain Maxwell equation. So let's go to start reviewing these theorems. The first theorems that I like to start is the fundamental theorem of calculus. It's the most important theorem, and what it says, the theorem, is that if you have a function f of x, and you want to find the area between a and v, the area, the integral from x equal a to x equal v of f of x ddx is equal to, so the information of the entire regions that stay as the area is codified by the antiderivative of the function f, capital F, evaluated at the points b and a. So f of v minus f of a. Then the information of the area is encrypted, is codified at the endpoints by the function, the antiderivative of f. And this is not the only case when the information of a big region is codified as the difference of the corresponding function evaluated at the endpoints. For example, the fundamental theorem of calculus for line integrals say that if the field f is conservative, meaning that the line integral, meaning that exists, is conservative, meaning that exists a scalar function f of x, yc, or f, such that the gradient of f is a vector, the gradient of f is the vector field. And what it say, the theorem for line integral, the fundamental theorem for line integral, it say that if you have a vector field f which is conservative, so it exists little f such that the gradient of f is the vector field f, the integral, the line integral from x, from a to b, from r equal the point r1 to r equal the point r2 of f scalar ddr, the line integral of the vector field along the curve ddr from a to b, or from r1 to r2, is equal to f of b minus f of a. Wow! Is the information about the endpoints, the information about the endpoints, this is the point A, this is the point B, this is the vector field f. The vector field f is going in some direction, and you are calculating the line integral of f ddr along the curve, and the information about the line integral is codified about in the endpoints by the function f, which is the potential, sometimes called the potential. The difference in the endpoints of the function f will give us the line integral. But this is not all. This is not all. We may talk about the Gauss theorem that is quite different from the Gauss law that we will see for Maxwell equation. The Gauss theorem relates a line integral over a curve, but now it's a closed curve of the vector field f scalar ddr with a double integral over a region. What region? The region that is contained of C, this region. And what it say, Gauss theorem, it say you can find the line integral of the vector field f scalar ddr over a curve. So now the vector field is not conservative because the line integral will be 0. And the connection is that you connect a line integral with a double integral to the region R. Of what? Not of f. Of f will have two components, fxi plus fyj. The derivative of fy respect to the x minus the derivative of fx respect to the y, ddx, ddy. And again, the information in the region R is related with the line integral in the boundary. Wow. But this is not all. This is Gauss theorem, and Gauss theorem allow you to draw any path and to say what is the area inside. The area enclosed by the path. This is something that I was always impressed. When I was young, my neighbor, he was a topography, and he went to the land to measure the amount of land, the square meter of lands. He will drawing the border, the frontiers of some lands, and finding the area. How he will find the area? He will say, let's go to choose the vector field f, like the vector, let's go to try if this will 1, minus y I plus x j. If I use this vector field, Gauss theorem will say that the derivative of fy respect to the x is 1, and the derivative of fx, the component x respect to the y, will be minus 1, so this will be 2. So let's go to consider the vector field 1/2 of this. So now, instead of to calculate the area of f scalar ddr, Gauss theorem, it say the line integral of f scalar ddr over the closed curve is related with the information that is inside the boundary. How we relate it with the double integral, the area. And what will be the area? The area will be the derivative of fy respect to the x, which is 1 minus 1 plus the derivative of fx respect to the y, which is minus 1 plus 1. And because I have this 1/2, this will be 1. Divide by 1, ddx, ddy. Wow. So the line integral of this vector function f ddr, the line integral of f scalar ddr for this particular vector function will give the area enclosed by the curve. Incredible. Incredible how to do this. Now, let's go to write another theorem, the divergence theorem. The divergence theorem relates the flux over a surface, a closed surface, to a triple integral over the entire region, the volume inside the surface. So in some way, the surface will be the boundary, and inside the region is the volume. So exactly what it say, the divergence theorem is here. There is a flux F scalar dds. So the flux of the vector field F scalar dds, F scalar dds, if F goes in this direction, and the normal of the surface goes in this direction, so F scalar dd area, let's go to put it like this, the flux F scalar n dds. Now, the flux of the vector field, the flux that going out of the volume, is related in a closed surface, is related with the function that is the divergence of the vector field, and is the triple integral over the volume of the divergence of the vector field. And the divergence of the vector field is a scalar function. And the divergence, the flux per unit of volume, multiplied by the volume, is the flux going out of the surface. So we relate again information about the boundary, the flux that going out, with information inside by the corresponding function that in this case is the divergence of the vector field. And the divergence, we will study carefully how to obtain the divergence. The divergence is defined as the limit. The divergence is a local, is defined at a point. The divergence is the limit when the small volume ddvi goes to 0. So we imagine around the point a small volume ddvi. Right? So it's the limit of the flux. The flux of the vector field is F scalar n dds, dd area. dd area, maybe I should use instead of dds here, dd area, dd surface, but it's better to call dda. Now it looks better. Okay. So what we have said about the divergence theorem is that the flux across the surface of the vector field, the double integral about a closed surface S of the vector field F scalar dda, or if you prefer, is F scalar n unitary by dd area. This flux of the vector field is related with the corresponding function over the volume that is the divergence. Then we can write that the divergence of F, a number, an scalar, over the volume, the sum of the value of the divergence of f over the entire regions, over the entire, is related with the flux, with the boundary conditions. And what I was saying before, that the video stopped, sorry, my camera, is that the divergence of a vector, of a field, is defined at a point as the limit when the volumes goes to zero of the relation between the surface, the flux per unit of volume. Then the divergence of a vector field is an scalar functions that depend on the point that you are considering. So if you are inside the volume and this is the vector field crossing the surface, and you consider this point to measure the divergence, what you do is that you imagine a small sphere around the point. You measure how much is the flux, the total flux, the net flux of the vector field around the surface S, and the relation between the flux per unit of volume, when the volume goes to zero, it measures the divergence. And what the theorem says is that if you sum all the divergence through all the points inside the volumes, so in some way you fill the volume with many, many small volumes like this, you take the volume to zero, the total divergence, the sum of all the divergence per unit of volume but multiplied by the volume will be the flux going out of the surface. So we will make a proof of this theorem, and we will do examples to convince ourselves that these have sense. So the last theorem that I would like to describe is the Stock theorem. The Stock theorem, it says like this. First of all, let's go to define what is the curl of a vector field. The curl of a vector field measures the tendency of the vector field to rotate. So the curl of a vector field is the circulation over a curve C of f scalar ddr, but now is per unit of area. So you have, this is the theorem, it's Stock theorem. You have a curve C, and you have a vector field F in the space. Imagine a vector field. You construct now a surface that is supported on the C curve. Any surface will work. And what the Stock theorem say, it say that the line integral over the closed curve of f scalar ddr is related with the flux, wow, over the surface, wow, over the surface, this surface, dda, not of f, the corresponding function. The corresponding function is the curl of f. The curl of f is scalar, the normal vector n. dda, this is a Stock theorem. It says more or less that the tendency to rotate through the circle is the same tendency if you divide the surface into small regions, and you consider the circulations over every small region. The curve of F measures the circulation per unit of area. If you multiply the circulation per unit of area by the area, okay, one thing, and this is done in the limit when the area A sub I goes to 0. So what it say that the tendency to flow, to rotate of the vector field around the surface is exactly the same as the line integral of the vector field around the curve. Not easy theorem to practice, and we will use it in connecting with electric and magnetic field. So now let's go to talk about electric and Maxwell equation. What it say about Maxwell equation? We say that we have a pair of vector field. What are the vector field? The first vector field is the electrical field, and the second is a magnetic field. And these are vector fields that are like brothers. And these are particular vector fields in the sense that, for example, if you have a charge, the charge will produce an electrical field at some distance r, and the electrical field will be radially, and the electrical field E depends on the amount of charge that is here, Q, a constant K. The constant K, most of the text write like 1 divided by 4 pi epsilon sub 0, when epsilon sub 0 is the permittivity of the vacuum, and the electrical field, this have a magnitude, and the magnitude depends on the distance square from the point P on observation, and it goes directly radially. So it goes in the radial direction. So this is what Coulomb's law say about the electrical field, and what Maxwell equations say. It say like this: if you construct any surface around the charge Q, and you measure the flux of the electrical field around this charge, the flux, the integral over the surface, the closed surface of E scalar dDA, and dDA, the flux is always equal to the charge divided by epsilon sub 0. So the amount of flux that will come out of the surface is related with the amount of charge that is inside the volume. What is the charge? The charge is not easy to define. A charge is an attribute. It's the attribute that a particle have to create an electrical field. So how we connect this theorem that is, say, Gauss law, no Gauss theorem, Gauss law, that is the first law of Maxwell equation. How we connect it with the Gauss theorem. We will say like this: a double integral is related with a triple integral by the divergence theorem. So the flux, the integral of E scalar and dda is applying the divergence theorem is the triple integral over the volume of the divergence of E ddv. So if we compare these two equations, and very important, if this that I have said is valid for any kind of surface that I construct around the charge, then the first Gauss law, the first Maxwell equation, will say that the divergence of E is rho divided by epsilon sub 0. Why? Because for one side we have that this flux integral of E scalar dda is equal to the charge divided by epsilon sub 0. But the charge is the total charge that is inside the surface, the closed surface S. And the total charge that is inside in the closed surface S is the integral of the density of charge, the charge per unit of volume, by the volume. The charge per unit of volume multiplied by the volume, the summation will give the total charge Q. So Q divided by epsilon sub 0 is the flux. But we have seen that applying the divergence theorem, this is equal to the triple integral over the volume ddv of the divergence of E. If this is true for all volumes, for all surface, what we have is that the divergence of E, that is a number, is a function that is a scalar function, the divergence of E is rho divided by epsilon sub 0. And this is the first law of Maxwell equation that we will do more practice about this. Let's go to the second law of Maxwell equation. The second law of Maxwell equation say like this: there are charges that produce electrical field, and now there are currents. There are currents that produce magnetic field. They are different vector field, and they act on charged particle in different ways. For example, an electrical field will make a force on a charge Q by Q by E. So if you put the charge Q here and there is an electrical field here, the charge will be subject to a force in the same direction as the electrical field, and the amount of force that we will subject, the charge Q will be Q by E. For the magnetic field, so this is the electrical field, for the magnetic field, the force is a little bit strange. If you have a magnetic field B here, and you place a charge Q here, to observe force on the charge Q, you need that the charge should be moving. And if the charge moves in the same direction as the magnetic field, the charge will be not subject to any magnetic field, any magnetic force, because the magnetic force is Q V cross V. So you need to observe the force produced by a magnetic field. You need the charge Q to move in some direction that is not parallel to the magnetic field, in a way that there will be a force. The force will be B cross B. So the force B cross B, B is going in this direction, the magnetic field. The force B cross B goes to your eyes. So it's a force that generates acceleration going to your eyes. So the charge Q will observe, will be subject to acceleration in the direction going to your eyes. Okay, so what happened with the second law of Maxwell equation? When you have a magnet produces magnetic field. So it produces magnetic field. And the magnetic field are closed paths. Wow! So if we wonder, the magnetic field goes in this direction, let's say, well, first, how is produced the magnetic field? Because the magnet have currents. Otherwise, you cannot produce magnetic field. So you have to accept that inside a magnet, there is a flow of currents flowing. And these currents will produce magnetic field. So inside there are microscopical currents, and these microscopical currents will produce magnetic field. And this magnetic field, if you wonder what is the divergence of P, the divergence of E is the density of charge divided by x equals to 0. Well, the divergence of P is 0. This is the second Maxwell law. What it means that if you place a small volume here at any point that you can imagine, even if you place it here inside the magnet, the flux that goes around the surface, around all the surface of the object that you have installed, V scalar dDA per unit of volume will be 0. What it means is that the same flux that is entering the volume, the same flux that is entering is going out. This is why in physics they say there is no monopole magnetic charge, because for electrical field the divergence is produced by the density of electrical charge. For magnetic field there is no magnetic charge, and the divergence is 0. So for the moment we have two Maxwell equations. The first Maxwell equation, let's go to write it in two different forms. In the first form, we write it in integral form, and it will say that the integral over the surface S of E scalar dds will be dDA, better, be dDA. E scalar dDA will be the charge divided by x equals to 0. This can be written in form of differential form, like the divergence of E equal the density of charge divided by x equals to 0. And the other theorem that we have is that the integral over a closed surface S of B scalar dA, this is always 0. And this means that the divergence of B is equal 0. So this is the first law, this is the second Maxwell law. Now the third law of Maxwell equation is even more interesting. Is the fundamental law that allow us to generate electricity. Electricity is very important in our lives. We don't imagine to live in the way that we live without electricity. And what it says, the third law, is called Faraday's law. Faraday's law says like this: if you have a magnet, and the magnet produces magnetic field, and you have a loop of a cable, and now you move the magnet with certain velocity v in a way that the flux crossing the surface S is increasing. So the flux of magnetic field is the integral of B scalar dds. And as the time change, the flux increase if you move approaching to this copper cable. So there is a change in the flux respect to the time of the magnetic field. So the flux is changing. What it say, Faraday's law, it say, wherever this happen, you produce an electrical field. And in the loop will appear an electrical field that is tangent, in this case of the symmetry, is tangent to the loop, to the copper cable, in a way that the law will say that the line integral over the loop C, this is Ct, of E scalar ddl equal minus the derivative respect to the time of the flux of magnetic field, of the integral over the surface S. This surface S is not a closed surface. V scalar dda. So it related the change in the flux of the magnetic field with the appearance of a new field that is an electrical field that now is not conservative field, in a way that the circulation, the line integral of E scalar ddl, it is directly related to the change of the flux of magnetic field. And the minus sign, it say like this: if the magnet is approaching the cable, the copper cable, so the flux is increasing. So the change in the flux will go to the right. So the change of the flux is increasing and increasing because there are more lines of magnetic field going through the loop. So the minus sign refers that the electrical field induced will oppose to the change by creating an electrical field that will oppose to the change. So if a change in the magnetic flux goes to the right, the line integral, the electrical field, will be in such a way that E scalar ddl will go to this, will oppose the E scalar ddl if you use your right hand to to make easy to understand it, E scalar DDL, you take your finger over the loop and your thumb will point in this direction. So this is the correct direction that you induce the electrical field. Well, indeed, the electrical field will go in this direction, in the opposite that I have drawn. It will go in this direction, in a way that E scalar DDL will generate, if you take your hand and you put your hand over the loop, your thumb will point it to the left, okay, opposite to the change in the flux, in the magnetic flux. If you, instead of approaching the magnet, you go and you move the magnet in this direction, now the flux will change, but decreasing. So the change in flux will go in this direction. So you need to induce an electrical field that will produce a magnetic field, because here the electrical field produces a current, the current produces a magnetic field, so that it will be opposed to the change. So it will go, the E will go in this direction. Not easy law. And this is the way we produce electricity. We produce electricity by changing the flux of magnetic field over certain loops, creating an electrical field. The electrical field will produce a motion of the free charge that are on the copper, and the free charge will move, and we will have currents. Wow! So the current that you receive at your home is produced in this way. And the last, so this is the third Maxwell-Faraday equation. Let's go to write it again. The third Faraday law equation, it says that the derivative respect to the time of the flux of magnetic field over the surface S, not closed surface, V dDA is related with the appearance of an electrical field E whose circulation E scalar DDL is exactly the change in the magnetic flux. And if we want to write this in differential form, will be achieved by this is C, is a closed curve of E scalar DDL. So if we apply a Stokes theorem to this part, this is the double integral over the surface S, not a closed surface, of the curve of E scalar n, the vector n, dDA. And now I can compare this part with this part. So let's go to put this part correctly. So the derivative with respect to the time t of the integral of V scalar dDA can be written as the integral over the surface S of the partial derivative of V respect to the t by dDA. And if I compare with the same integral surface, the same surface of the rotor of E, scalar n dDA, I can say, and there is a minus sign here, I can say that the rotor of E, the curve of E, is equal to the minus the derivative of V respect to the time t. So the third equation will say that rotor of E plus the derivative of V respect to the t equals 0. And this is the third equation of Maxwell equation written in differential form. Here there is a detail. If I say that this is equal to this, the integrand that is here should be equal, because this is valid for any surface. So the integral must be equal. So this is the third law. And now let's go to the fourth law and we finish. I'm sorry that it delays so much to explain this. And the fourth law of Maxwell equations, it says, wherever you have currents, you produce a magnetic field. So imagine you have a current I, and you produce a magnetic field in a way that the line integral over the closed curve of V scalar ddl is mu zero, a constant, that is the permeability of the vacuum by the current E. What it says Maxwell is that this law is valid when the current is constant. If the current is not constant, it varies with time t. He adds as an additional term that is mu zero x sinus 0 by the derivative respect to the time of the flux over the open surface, not closed surface, of E scalar dds. So now he say like this: magnetic field and electrical field, they behave like this in the same way. Wherever there is a change in the magnetic field, the third law, when there is a change respect to the time in the flux of magnetic field, there is an electrical field E produced. Now he say, now when there is a change in electrical field, should appear a magnetic field. So this is what this term that he added, just this term is called the current of displacement. This term, I sub d, current of displacement. This term he added by trying to make symmetry about the behavior of the electrical field and the magnetic field. Let me put it here: E dds, B scalar ddl, E ddl. So what we have now is that this term allows us to have electromagnetic waves. This term is the term that will allow us to find a wave equation. And my wave equation will say like this: the derivative of E sub x, the component x, the second derivative respect to x, equal 1 divided by c squared by the derivative of E sub x respect to time. And we will have a wave equation using only this term. And imagining that we are in the space in vacuum where there is no current, the current will be zero. We will do this and we will show how it's possible to obtain a wave equation. So how do we write this equation in differential forms? So we will transform this line integral into the line over a surface S of the rotor of the curve of B scalar dda by Stokes theorem. So this will be mu sub 0 by the I is the current, but the current is the density of current, the current per unit of area, by the area. This is the total current, because if J, the vector J, is the density current per unit of area, multiplied by the area, it will be the total current. So the fourth law of Maxwell equations say that the line integral that we have converted into a surface integral will be mu sub 0 plus mu sub 0 x sinus of 0 by the derivative respect to the time of the integral over an open surface of E scalar dda. E vector E scalar dda. From here, I can write the differential form of the fourth law of Maxwell equation. Will say that the curl of B will be mu sub 0 by J, the vector, the field vector curl of B. So you have B and you have the curl of B, that is a new vector field. It will be the sum of the vector field mu sub 0 multiplied by J, by the vector field J, the density of current per unit of area, plus mu sub 0 x sinus of 0 by the derivative. If I place the ddt inside the integral, will be a partial derivative by the partial derivative respect to the time of E. So I have made that the integral will be all the same. But why I can do this? Because the S could be any surface S, any surface. Any surface we sustain the curve C. Okay, C, the curve C, this curve C. And any surface. Any one that you can imagine. Okay, so this is the fourth law of Maxwell equation. And the idea is to work with these laws and with detailed explanation of the curve, of the divergence, of the gradients, to have these laws more sense. Okay, we finish here.